Hello students, welcome to Mathematics and Statistics channel. My name is Raman, and today we are going to begin a new topic on stochastic processes. Okay, I'm a TA at the Department of Statistics and Actuarial Science alongside with Ernest, and today's video, like I said, is going to be focused on stochastic processes. Okay, we are going to do the introduction to the course, and systematically we are going to give you like a chronological order as to how and what stochastic processes mean. So let's dive into the video and see what the course is really about. Okay, so first of all, we are going to look at this, the outline of our introduction video today. Okay, we first of all look at the definition of a stochastic process. The stochastic process, maybe some of you might have heard it before. The other name for it is a random process. Okay, anytime you hear of this, what it means is that a stochastic process is simply an infinite index collection of what random variables, that is x. We all know the negative binomial distribution, the Poisson distribution, which we introduced in the introduction to probability course. All we said are random variables. So this time around, the narrative is going to change a bit. Okay, so we're trying to say that the time is a random variable anyways, but it's dependent on time, as in this time can actually be it is defined over a specific domain. You've learned from the other distributions like the Poisson, negative binomial, Bernoulli, geometric, and so forth, that every distribution, when you realize it, it has its own domain. The domain, the set of values that the random variable takes, is very important. So the same way here, this stochastic process, the time should have a support, and the support is t. So t here represents the time, and it should be within some interval. Okay, so is the interval going to be continuous or discrete? Okay, so this capital T you see here is tau. So tau is the domain in which this time that we are taking, okay, the index time for the process, is what is going to come from. Okay, so this is normally defined over a common probability space. Okay, like I mentioned, the index parameter time, or t, is typically the time. Okay, but sometimes in physics, in application to physics, it can be a spatial dimension. All right, random processes are used to model random experiments that evolve in time. For example, if we want to receive sequence or wavelength at the output of a communication channel, this can be seen as a random process or a stochastic process. Secondly, packet arrival times at a node in a communication network is also another example of a stochastic process. Thermal noise in a resistor, for those of you maybe who have physics background or you've heard of resistors and so forth, they can all be seen as what are stochastic processes, right? And most importantly, like daily price of a stock, like forex trading, stock prices, and so forth, they are all like random processes because they depend on time. You record the process, maybe what is the when you do exchange, like what's the name, forex trading, every minute or second you realize that the stock prices are changing per the time. Okay, so that's actually a very good example that like you can relate to as an example of a stochastic process, right? Now, there are certain questions that we need to know about like random processes or stochastic processes. Okay, so dependencies of the random variables of the process like are very important. So we want to know, like we know that to do predictions in the future, like we need past data or historical data. So stochastic processes actually want to answer these questions. So how do future prices of a stock depend on its past values? Okay, it can also be seen in terms of long-term averages, as in a queue we all find ourselves in, like daily activities, like you go to the bank, you form a queue and so forth. So we want to know what is the proportion of time a queue is supposed to be empty? You go to commercial bank, MTN office, and so forth. So what's the proportion of time like the queue is expected to be empty? Or maybe you want to know the average noise power at the output of a circuit. We all use circuits at our homes and so forth. So you want to know the average noise power at the output of that circuit, right? Another application can be seen in a stream or boundary events. Okay, so over here we want to know what is the probability that a link in a communication network is congested. Okay, then secondly, what is the probability that a gambler will lose all his capital? For those of you who do betting, you bet on sporty bet and so forth. So we are interested in the probability that you lose all your capital or you actually gain something. Okay, so that's an example of a stochastic process, right? Okay, so there are two main ways to view a stochastic process. Okay, so a random process can be viewed as a function of what? That's x of t comma omega of what? Two random variables. Okay, so one, you can see time, which we've already mentioned. So, and we said time belongs to some domain, that's capital tau, and the outcome of the underlying random variable, which is omega. So omega is actually like, if you are interested in modeling like, or the number of sales you make from your provision shop. Okay, so at what time, maybe let's say you are interested in the monthly sales, like you are going to take daily sales to make your monthly sale. So day one is going to be like a stochastic process where you are modeling the sales that you are going to have. So let's say day one is actually time 1, that's the time index. So if that day 1 gives you, like, you are able to sell maybe 10 bags of rice, it means that omega is 10 and the time is what? 1, because this is the day 1. So if you go to day 2, the time is going to be 2, and then like let's say day 2 gives you 25, it means omega is going to be what? 25 as well. So now we can fix one, like if the time is fixed, meaning time is constant. By fixing time, we are trying to say that we hold it constant, and then once that happens, it means that the whole stochastic process is a random variable over what? Omega. Okay, secondly, when we fix omega, it means that we are going to have a deterministic function of only time. Okay, in other words, we call it a sample function. Okay, now to move on, we want to look at the description of a random process or a stochastic process. So in a random process, that's x of t, where we all know what the time is. So time belongs to some support. Okay, so t is called the time parameter, which we all know right now, and it is the parameter. Tau is the parameter set, which I've already meant, the support of the time, whether the time is going to be the set of integers, natural numbers, or maybe an interval. Okay, so x, that's each stochastic process, x of t, takes values in a state space, and the state space is what? The s. Okay, so s belongs to some real, is a real value. So let's put it this way: if we have a stochastic process, that's x of t is equal to I. So we say that the process is in what? Is in state I at time t, meaning from our daily stock, like what's the name, sales example. So if at time 3, that's on the 3rd day of the month, we are able to get give me a second, let me write something. Good. So let's say on the 3rd day, that's x 3, x3 is equal to 7. So what it means is that if on our 3rd day of our daily sale recordings, we are able to sell maybe 7 bags of what? Rice. What it means is that our state space is 7 and our time index is what? Is 3. Okay, yes, so that's what it means. So every stochastic process, you have what? The time index and then the what? The state space. All right, now let's get to the types of stochastic processes that we have. So we have discrete time stochastic processes and we have continuous time stochastic processes. So first of all, let's look at the discrete time processes. Okay, so when we say a stochastic process is a discrete time stochastic process, all that it means is that the time is going to take some set of discrete values. It's going to take some set of discrete values. So also called a random sequence, because we're going to be listing is like a sequence of like the time is going to be like 1, 2, 3, 4 and so forth, just like natural numbers. Okay, so over here time is going to be the set of natural numbers, integers or any other discrete values that you can think of. Right over here you can see that n is equal to 1, 2 and so forth. Okay, yes, so in practice, so t belongs to the domain, like that. T is the support. The support is going to be the set of natural numbers starting from 1 to infinity or wherever we end. Okay, sure. So that's a discrete time stochastic process can be seen as x naught. So x naught is the stochastic process at time 0. So x1 is the stochastic process at time 1, x2 and so forth, just like that. So a new random variable is generated. So this collection of random variables x0, x1, x2, x3 and so forth, all of them are seen as random variables, just like you learned in the probability review and the random variable lesson. Okay, so when we collect all these things together, you see we kept it in a curly bracket to show that this is it's a set. So this collection of random variables is what we typically call the stochastic process. So this is actually a discrete time stochastic process. So let's move on to look at the continuous time stochastic process. So the definition for it is similar to that of the discrete, but here is the case that time is the difference. Right here, this time is not going to be discrete, we cannot count it. Okay, we're trying to say that the time domain is going to be some real values is going to be on the real lines. For instance, an interval, so we can have values like maybe give me a second, coming. So we can have something like t belongs to the interval 0 to 1. So when I look at this interval, I can have 0.01 as a point. Okay, I can have 0.02 and so forth. So this is what we call continuous time. Time is continuous. It's not something we can count. Okay, we cannot count time this time around. So in that case, we call it a continuous time. So any stochastic process whose time is continuous or is on an interval, we call it a continuous time stochastic process. Okay, continuous time stochastic process. And we can see this one domain that t can take is 0 to infinity. Okay, 0 to infinity. This is an interval. Okay, or 0 to k for some known value, like known constant k. So we are moving from 0 to constant k. Yeah, so I've spoken about state space already, so let's give it a proper definition in this slide. So the state space S is called a discrete state process if it is if it is discrete. Okay, or sometimes we refer to it as a chain. All right, otherwise we call it a continuous state process. That means if the state space is going to be continuous. For instance, let's look at the stock prices. We all know that prices cannot be discrete. You cannot have prices to be like 20, 30, 50 and so forth. Sometimes you can have 20 cedis, 50 pesos and so forth, or maybe 1 cedi, 10 pesos, 1 cedi, like 70 pesos and so on. These are not discrete in nature, they are continuous. Like the state space, the output we get is continuous in nature. So in that case, we say that the type of stochastic process we are dealing with is a continuous state stochastic process, meaning the state space is continuous in nature. All right, let's move on to look at some important functions about the stochastic process. When you learn distributions, yes, so in our next video we are going to continue with some statistical properties of the random processes or stochastic processes. So for now, we end our video here. Thank you so much for your time and patience. God bless you and have a nice academic journey and studies. Thank you.